this last talk is about how to start writing an agent yourself. So that we'll go straight into the paired programming session afterwards. So that's what I'm going to talk about. We'll start from an example project that we've created, which is called C-filter templates. It has got everything set up so that you can start working with a C-filter-based agent. Then I'll go over some of the code that's inside this template so that you know how you can work with it. I'll highlight the important bits of the existing sine oscillator so that you can kind of inspire yourself from that code to build audio agents. And then a little bit at the end about how to distribute the agent that you created so that you can share it with the community or even sell it, since they're binary packages now. So how do you start? There is a new Git repo here, which is eigenlabs/eignd-example, where you can actually get this example project from, which at the current time has one template project, which is a C-filter template. Over time, this will probably accumulate other templates and interesting projects you can start working from. So it's got a number of files in there. Those files are basically not that important. So the --init underscore init underscore thing is to make it a Python module. And then you've got two basic build files, one for Windows, one regular make file, so don't really have to look at those. This is the first interesting file that actually ties into the sconce build system that we use to build Eignd and the agents that you create with Eignd. Then we've got a .pip file. A .pip file is the file that you use to actually create the bindings between the C++ and the Python world. And this is really automated, so it's basically a description of the API that you want to export. And then the build system will generate the required C++ files for that and compile those so that Python can actually use that. And then the actual implementation of the agent that you're writing, which has a Python wrapper around that's kind of the external world, and then the actual implementation underneath that's written in C++, which is not necessarily needed, right? So how do you build this? Probably the first thing you'll want to do, you check this out. And if you have Eignd 2.0.35 installed, which is now available on the website, then you don't actually have to check out the whole repository from GitHub. All you have to do is install 2.0.35, and then inside the installation directory, this on Macintosh and this on Windows, there is a tools directory which contains everything that you need to make the build system work.
That's the 2.0.35 release. It's not. You know, it's not
yes.
GitHub, it's the release.
Yes, the release, yes, yes. But you'll find that in GitHub also. There is a tools directory in GitHub, which is basically the same. It's the same, right? Yeah, basically the same. You never know, right? And so once you've done that, you've actually copied the build system into your local project. And then you can use make or build.command on Windows to actually create your agent. So once that's done, it will create your binary agent, and it will you will be able to configure Eignd to actually see this agent in your local directory without installing it to user.py. So what you need to do is to change this file. There's a new file in your user's Eignd configuration directory, which contains your setups and which contains all the usual Eignd state. There's a new file in the global state, which is paths, where Eignd will look for additional agents that are present on your system. So what you basically have to do is this path here, so this is wherever you started the project checkout from GitHub, this path /temp.plugins will be added to the paths.txt file. And once you've done that, you can start up Eignd. It will detect that agent, and you'll be able to work with it. So basically, you'll see this example pop up here in the Create Agent dialog in Workbench, and you will be able to use it by wiring it up straight. So this is very convenient because you can just continue working on the project that you've got in your user's home directory or in your workspace. You don't have to install it all the time. By adding that path to the paths.txt file, you can just iteratively make changes to it and test it And then once you're done, you can distribute it and install it for real. So that's a small overview of how to start with C-filter template. Now let's look at what this template looks like.
Just one question.
Yes.
In the GitHub code base, you've got a separation between the Python code and the C++ code. Obviously, Python sits above the source directly.
Yes.
Is there any particular reason? Is that a good model to follow, or do you? I mean,
there's no particular reason to do that, apart from when you start having a lot of files in the implementation, to cleanly separate it out.
Yeah, I mean, we have some directories which are multi-purpose. They're C libraries or C++ libraries, as well as Python modules, and typically the actual implementation of the library goes into a subdirectory. That's the only reason. Inside a plugin directory, I don't really see the
It's idiom. There's no technical reason.
No, I just wondered, was it an idiom that you wanted to propagate?
It'd be nice if it's just for consistency, if it's sort of was the same, but
Fine.
So the question you just said about iterative development there. If I'm changing the C code recompiling, if I delete an agent and reload it, does it reload the source code, or do I have to stop the Eigen?
No, you have to stop Eigen.
You have to stop Eigen,
yes.
so there's no dynamic reload.
no crash.
But at least you don't have to go through the install process, which is
No, I was just checking how far along that
or
line
copy
we
files along, and so.
Okay, cool.
So this is basically what you do in the Python shell. So when you write an agent, you've got the Python version of it that is kind of the entry point into the agent, right? So it's got the metadata, it declares the ports, sets up the clocking, and any other configuration that you want the agent to do to live inside the Eigen ecosystem. And this is about the most basic agent that you can write. This is a fully functional agent that has no ports, but that will show up in Workbench, and that is actually ready to use, but it doesn't do anything. Right? But it is interesting to see that this is the boilerplate code that you actually have to write. There's this piece here that you might wonder about. It is generated by the build system. So in the script.first file, you will indicate, I will go over that later, you will indicate a version that then will be generated into files that are being compiled by the build system and are available here to be imported inside the Python code, so that you can pass that version along here in the signature, and then you will see that appear in the C version metadata of the agent, right, Jim? So that's then what is used by the upgrade mechanism later on. If you see that an agent that has been stored by the state manager with a particular C version, then, and you have this agent that might have another version when it's loaded, then the update
so you have to do that. You want it to play nice with the upgrades, you have to do that.
Yes. Well, it's when you make significant changes to an agent that require updates, basically.
Is there a mechanism in place for doing that upgrade, or is that completely necessary?
No, there is a mechanism for doing. There's an upgrade tooling system that allows you to go through several phases of doing the upgrades. There's also an upgrade system. This is not. We're not going into that now. But it's interesting to know about. There are several levels of upgrades. There's upgrades that basically just run bel canto to modify an existing setup so that it can run with new agent, while there is another system for the updates that actually can execute C code or Python codes to do more dramatic changes and kind of change the state variables directly to change your state before the agent is actually using it. So there are different levels of working with that based on the kind of changes that you made to the agent. So this is where you start writing your code, right? So what do you typically do? So first you add this clock domain that will be used by the inputs and bundles so that they're all clocked by the same clock domain, and then the relationship can be built. So this domain is being used by the input, and it's being used by the actual C filter, the implementation, and is being used by the splitter. So that will split the signals back out so that they can go out through the output. And then there is another thing here that's interesting, and that is the cookie chain. So basically, in the opposite way around, an input is chained to the implementation by retrieving a cookie from the implementation here, which is then chained to the output by retrieving a cookie from there also. So this is how they're actually delegating to each other.
So can you just explain that a bit further? How does that cookie thing work and what does it do?
It's basically a token that is handed out,
Yeah,
right? So that they're able to identify.
It's the way the processing
upstream,
graphs are created.
Yeah. And that's what it drives. Is the
Yes.
processing graph.
Yes.
Yes.
The graphs are always created from furthest downstream, working upstream.
And the cookie is passed backwards from furthest downstream
Yes.
upstream.
Yes. So you create the output first, by retrieving the cookie from the output for the filter itself.
And so in the next phase here is, so you set up this vector input, and then you will create the atoms that are actually the ports into which the connections will be made with the various policies. So here you've got an isostream policy, which is what Jim already talked about. If you've got a volume input, basically this is set up to be an oscillator. The volume will be isochronous, so that is sample correct with the audio. And then you've got a frequency input, which is merge policy, which will merge onto this. This is a special policy that you also mentioned before, the local policy, which basically, if nothing is connected to the volume input, it will have a default value. If something is connected to it, then we'll take the fast data, and it will actually start generating the data from, accepting the data from the fast data. Yes, and it will ignore the default value. So the default event that the correlator will send to it through the local policy. And so apart from that, you've got different domains that you specify, which is basically very specific to what kind of input that you have. So volume input goes from 0 to 1 for the gain. Frequency goes from 0 to 96K. And then another interesting part here is the actual signal identifier, which ties into the declaration of the input here. You say which signals that the input can actually carry. And these are the ones that are then actually set up by the policy. So the policy that gets that also from the input. So the policy is created with input being a factory, and you pass it in the signal number that then will be relevant for that particular port.
And that numbering scheme is specific to this agent? For
this agent, yes. So typically what you will do is you'll factor that out into some kind of static variable or
So
constant, or you name them and then you reuse them, right? So this is up to you.
That's essentially a contract between the sending and the receiving agent. So I send on a certain signal, and the receiver has to know on which signal this.
No, because you will connect these together through connection. It's basically to identify the different signals that go in. That are.
Remember, on a bundle, each event in the bundle carries a number of signals.
Yes.
So we're configuring the input to say that each event that it's going to generate down the bundle is going to carry two signals, number 1 and number 2.
So the absolute number does not matter so much. They just have to be different.
Yes, it's so that you can later on in the implementation refer to it to extract data from the event. So you know that you will receive on signal 1, you will receive volume data. On signal 2, you will receive frequency data. Whatever you sent out there again through the output is another signal that's not specifically related, right? So
the indices on the self. So we've got self 1 is the output, self 2 is the input. The atoms on self 1 and self 2 1, self 2 2. Does that have to match the signal numbering?
No, they don't have to
So it's
match.
just simply a list.
So
That's what you see in BCAT.
Yes.
Those numbers.
Yes.
That's the hierarchy.
It's basically such a tree that's built. You can do whatever you like there. Something that we've started doing here is with inputs to have this hierarchy. So there are still some agents where you have, instead of having 2 and then 2 1 2 2, it will be 2 3 4 5 6 7. What you get then, if they show up in Workbench, for example, then since they're alphabetically ordered, then you can have outputs and inputs being matched together, and it's not that nice to look at.
You don't have to declare the number of elements underneath the tree.
Yeah.
It can change at any time. You can add them in on the fly, take them out on the fly.
So, then the final thing that you have to do to make this work, of course, is to add some Python imports. And this is what will be generated by the pip file, right? So it is a Python module that will be generated based on the code that you write in the pip file, which
you're going to name that. So that you're going to name that. You're going to make that file, right?
This is generated by the build system.
By the build system.
By the build system. After it finds the pip files, when I get in there.
Yeah.
So essentially, if I have a Python-only agent, I don't need a pip.
You don't need the pip file, and you will not be. You see, the C-filter template native is what's being used here to actually instantiate in that namespace a class called example, which has then the C++ implementation and gets the cookie passed in and the clocking domain.
Are these files generated in the source directory or in the source directory?
No, there's generated in the build directory.
The build directory.
Yeah.
You'll see a temp directory being created, and all the build products are down in the bowels of that somewhere.
Yeah, I'm just checking it's the same.
And they're basically just some other packages that are installed together with Eigendie that provide you, basic building blocks like clocking domain, the atoms that you instantiate, the policies, the bundles. And these also correspond to the .py files that you can find if you go to the actual Git checkout of the source code, where you can find more different policies that you can work with, different types of data types that you can work with the atoms. So if they're bounded integers, or if they're floats, or if they're bools, or all these things, then you can find them there. So this is the example of the C++ declaration that you will find in the C-filter template, which is very basic again. What you have here is that cookie that is being provided by the implementation, so it can be passed on, and it will also receive this cookie so that it actually is able to send data out to the output. And then what you get here at the bottom is basically a technique that has been developed to hide the actual implementation behind forward declaration of the impl_t class. You'll find that all around the system, so that the API of the actual implementation doesn't bleed out into the actual declaration here of the agent, which keeps it nice and clean and makes sure that you're not relying on something that you don't want to expose. Right? And this is how you set up the pip file. So the build system passes these pip files and creates this Python to C++ wrapper. This is the example that you'll find in the template. You can see that it's quite simple. The only thing that is important really here is that you only have to export the APIs that are meaningful to the Python world, right? If there might be some methods in there in the header file that are used by other C++ classes. If you don't want them to be available in Python, then you just don't declare them here. And for the rest, these kind of mirror the namespace. So the example T class that was created in the C-filter template namespace, you give it the Python class that will be used, and then these are some imports from the actual Eigendy installation that you will find in user.py. So there's a whole bunch of Python modules installed.
Can I add something quickly there? The way that it's written, the way that these wrappers work, we have PIW is one of our primary libraries, and it contains lots of components, lots of bundle components and things. There's a wrapper for that, piw.pip, which wraps the Python parts of that class. Now, if you define a class that extends a PIW class, you can define a wrapper that will extend the PIW wrapper in turn. That's how this import mechanism works. So if you have C that expects a PIW class and you derive from that class, you can take that in Python, take the Python instantiation of it and pass it to that C, and it'll all work quite nicely. That's kind of why we're using this particular wrapper generator for primary reasons, so that we can extend wrappers like this.
And that gets us into the guts of the thing, which is the C filter. So the C filter is handy because it does all the event handling. You just get the signals, you know when events are get started and stopped, and you process the data that's relevant and then generate the data that you want to output. So this happens at regular clock ticks, since it's a clocked filter, right? It's got a whole bunch of convenience methods to allow you to handle the input, the data input and data output, and then you can declare which signals it accepts and which signals pass through. The only real limitation is that you can't synthesize new events or drop existing events. It's kind of a one-to-one mapping to what comes in, what comes out. So this is what C filter looks like. In this case, so the implementation extends the C filter class and implements the C filter controller by adding the methods here at the bottom. But what it basically does to the C filter class, it passes itself as being the controller, and then it gives the cookie, the output cookie and the domain to the C filter, and then C filter will do all difficult parts about the event handling, right? And it will call back into the controller that you passed in here to kind of kick off everything and get its required configuration. So that's what happens here. You declare which inputs you actually want to process. So these signals are the ones that you set up in the Python file, which were the volume and the frequency. And it's basically a mask that you pass in. So you have these handy macros that you can use to just basically generate those masks. This is the output signal that you want to generate, and then you can have signals that just pass through. In this case, there are none of those.
I presume SIG2 and SIG1 are macros, just 1, 2, 3, 4.
Yeah, it just goes on. I don't know until what, but it's 24 or something like that.
We do have some bundles that have 24 odd signals in.
That information also be retrieved
quite big ones.
from the Python side configuration, because I already said which signals I want to have as input.
Well, it could be that some of the inputs you want them to pass through, right? So you basically you have to say which inputs you actually want to process and which inputs.
So if you don't name any of them, they just become pass-throughs.
No, they'll just stop.
Yeah,
they'll just stop.
Yes.
Right, okay. Oh, because through is there.
Yes. And this is the actual interesting C filter control function, which will create a functor that will actually be instantiated whenever the connection and the wiring is being done. So whenever polyphony channels are being set up, it will create a new instance of that class. And then the methods of the functor class will be called whenever events appear. So that's the implementation of that. It's got 3 distinct methods. So first of all, an important part here is that it gets an environment being passed in, which allows you to interact with whatever state that the C filter manages. So it allows you to interact with the data that's being, the data inputs, to generate data outputs, to work with the iterator that is actually present there, iterating over the ring buffers that are being passed in. So this is the actual handle that you get into the functionalities that C filter provides. And the first function is very easy. When an event is being started, this is being called. You get the event ID being passed in, and then the return return value indicates if this was actually a successful start or not. If you return false, then it will stop processing of this event, and the event will end. So nothing else will be no other callbacks will continue.
So are you saying, so a new instance of this is created on each event?
No. A new instance of this class is being created on each wire that is being connected.
Yes. Okay.
So it's basically when the polyphony sets up, then...
so you might have 8 of them start with, but then if you're using more than 8 voices, suddenly it needs to create some more.
Just, you said if it starts up and it says this event, if it's false, you said this event won't be processed.
This wire won't be created as well.
The wire will be created because it's there to receive events, right? But this method will always be called when an event is happening on a wire, and then you get the option to actually return false and say I don't want to continue processing this particular event.
Okay, so is that method called when an event starts,
yes,
or when a wire starts?
When an event starts.
Yes, it is when the event, not when the wire.
Actually, what happens when the wire starts is this constructor.
Yeah.
Right?
Yes.
So that's what happens when the wire starts. And then once the event has started, you're going to start processing, and this is where the clock actually ticks. So you get some timestamps being passed in from and to, which gives the beginning and the end of the data values that are being processed during this clock cycle. Then you got some handy values that you'll probably use, which is sample rate and the buffer size that is being used by this particular clock and this particular isochronous process. And then you process the signals here, and again, you will be interacting with the environment, the C-filter environment, to actually work with that data. And you get the option again of returning a Boolean. True will just continue. Return false means stop the event, don't continue. And then there's the final method here, which basically is called when the event ends. And you might do some cleanup logic there. There might still be some data on the event, on the buffer also that you want to process. So don't forget that. You can also have some data in the start. Might be some data sent along when an event starts. You might want to process that. Not all implementations need it. Some can just ignore that and only process them. It basically depends on your implementation.
If I return false from either of the first two, is the third one triggered?
No.
Or are these all external events? These are all external calls. So if I was in process and decided to stop the event,
yes,
I wouldn't get an end call.
No, you wouldn't.
You'd have to do the cleanup code yourself.
Yes,
exactly.
Okay.
Event is called meaning that the upstream has
something
ended the
outside
event.
has done it.
Yes.
That's, okay.
You can continue processing after that end.
Yes, because you might do like
the tick. Well,
right. So but here you get the option of actually after that ends continue processing. If you return true, it means that this event will continue lingering on, and it will continue passing.
You still get process.
Yeah, you still get the process calls, which is how you get those linger events when you press the hold pedal after the actual event has started. It has to continue basically generating a sustain or whatnot.
So for Eigen keys, essentially an event starts as soon as I press the key, and then I can modify it, and if I release the key again, then the event ends.
Yes. So that's basically the C-filter framework. This is the important part.
The from and the to, the longs, what are they?
Those are the timestamps of that particular clock cycle.
Oh, it's the long
yes.
timestamps.
So you use those, for example, and I'll get into this in the next slide.
Your iterator will need those to crunch through the actual values.
So that's where we are. So how do you interact with the environment, right? So the C-filter environment that is being passed in. You got a bunch of different methods there. Those are the basic ones that you will be working with. There are some, just 3 or 4 more, but not as frequently used. So you can get the next input value in the buffer either by providing it a reference to a variable that will be filled in with the signal that it is found on the buffer. That is the next signal. Since an event could have many signals, you can use that then to detect which signal that value actually corresponds to. And it will, as long as you keep calling that, it will give you the next value until it reaches that timestamp, right? Which is basically the 2 in the process call. And then you've got another version of this method is where you pass in the signal, and it will give you the next value of that particular signal up until and including, I think, right? It includes that, up until and including that timestamp, and it will use the signal that you pass in. Then if you're only interested in the latest signal, if you don't want to process everything in between, this is something you typically do when an event starts up and you want to have a start value that might already be there at event starts. Something that happens a lot is just get the latest value that is in the buffer at that time. So again, you pass in the time here, and this time you will see this in the examples later. It is the timestamp that is attached to the event ID that's being passed in that you will be using there, and then you get the latest value for that particular signal. And another thing that is done quite frequently when an event starts up is the reset, which basically resets the iterator over the buffer so that you can start from a fresh slate at that point in time. So that you don't get any of the other data that might be buffered up in the ring buffer that might still be there.
The iterator is bound to the input, not to the data buffer itself. So if two agents are reading, they don't influence each other's iterator.
No, it's separate.
That's true.
It is true, but it's independent for each line, right?
Yeah.
Yeah. So it's
the iterator is not part of the data buffer.
No.
The iterator is outside.
So, and then the last method that you will be using is to actually put some data for a particular signal out through an output of the agent. Right? And this is how you typically might be using it. So this is kind of a filled-in implementation of that process function. So you create a data type, which is an eigendata data type. There's a fast allocator that is present that allows you to create, so it pre-allocates a bunch of memory that you can then use to actually instantiate the variables from and then fill them in.
This is locked memory, right? This is memory.
Yes, this is locked.
Yeah,
but you can have locked memory or non-locked memory. Typically you will use that as locked memory on the fast thread.
Be gentle with locked memory.
Yes, don't, because there's a limit.
Use oodles of it.
Yeah, and it sticks around, right? Yeah. So in this case, since we're generating audio, you pass it in the timestamp, right? This is the 2 that you got from the process method, which will be the timestamp that's attached to that particular data value. You give it the size that you want, then you give it a buffer of floats that you will actually be filling in, right? So it will allocate that for you, and then the scalar value that will also be attached to the data value, which is, I think the scalar is the thing you see when you bcat something, right? So each.
Well, it's actually the.
So we've got a vector and a scalar.
When this buffer is anisoized, typically that's the aniso value, right. The value that's used for aniso.
Okay.
It's the.
So in this case, I'm just zeroing this out. This is an audio buffer. It's nothing in it. Zeroing it out, and I'm setting that an ISO value to 0. It's not really meaningful here. And then you iterate over the signals that are in the buffer. So you've got the signal variable here. You've got the value that things will be filled into. Those are references that are being passed in. So they will be filled in here. And then you have basically a switch that processes the signals. You do whatever you want with each signal. Probably you'll do some more processing at the end. And then once you're done, you use the C filter and output methods with the signal number again to output that data value out of the agent's output. And that will then go on the queues and be passed on to the next agent that's connected to the output.
This block of data is just continuous data, so I can even use it in a placement new for some utility classes that exist, or can I only handle it with specific data structures that are aware of the structure of this buffer?
This buffer is a continuous piece of data, right? I think it is.
Well, that's something. Supposing if we're running a buffer size of 512, then that
will be 512.
Yeah, that buffer out will the buffer out will be a pointer to the 512 floats that are allocated in that buffer.
So it's a C pointer.
Yes. It's just do whatever you like. Yes, you could placement view. There is a blob buffer type which you could then placement new or something to get a structure in there. Do remember that you are going to be putting this out, and we don't usually encode binary and stuff really into buffers, but you could. You might be better off using dictionary and tuple types to.
That's what I was essentially wondering, why there are specific data types, data structures for handling non-blocking.
Well, we're trying to preserve some sort of. Remember, this is a network transparent protocol, so it might end up on a system with different endianness or or something like that, you know, and it would need to get translated. If you're sending a blob out, then
I think you're asking about the NB part. Is that what you're asking about?
Yes, actually there is.
So there's a version that hasn't got the NB, and there's one
corresponding things that usually have an SCL, but there is a special NB map and NB vector and things like that.
Well, they basically changed the memory allocator so that when these maps are being allocated, it will go into it will use the fast allocator.
So they do not much more than just using the normal SCL classes with this buffer.
Yes.
So what kind of size buffers are you recommending people doing? You know, what's
well, the buffer here depends on what you set your
No, I know, but
you're stuck with that.
What's the rough, you know?
What's what you're set with in the audio interface, isn't it?
Yes. But typically, this is just a normalized data array, which will contain values from -1 to 1.
Right,
but you have
there's a clock tick that's going to...
Yeah, so this clock tick will call back in here, and will pass you in the buffer size that the clock tick expects to receive, right? So
that's what I do.
Yes, and this is then what you use here. But it's just one of the data types.
Yeah. So it's saying there's X amount of data.
Yes.
It's kind of set by the user, so it's...
Yeah.
I thought it was something you were compiling in, which is why I was confused.
But this is just one of the data types, so there are a bunch of other data types, you know, floats and tuples, dictionaries, that you can use as that will tie into the same memory allocation scheme, and they also have a structure that is set up so that they have a normalized and a denormalized value, so that if you connect one to another, it has some kind of way of determining how to transform a certain data type into another data type. So, well, not getting into that here, but you will see that you will come across a whole bunch of other data types.
We do jump through a few hoops because one of the guiding principles is that you should be able to connect anything to anything else. I'm not sure we're entirely good with that at the moment, but we're pretty good. So we do a lot of things to try and make sure that when you connect one wire, one pin to another pin in Workbench, something interesting is going to happen. It's not going to crash. So and hopefully something interesting and useful is going to happen. It doesn't always be. It's not always the case, but
it's quite tempting also to carry things to say completely normalize -1 to 1 or something like that. But you find, especially with frequencies, that the arithmetic error you'll get in the scaling is enough to throw everything completely off. So we do, most data is actually carried with its proper value. If it's a signal that goes from 1 to 1,000, it carries 1 to 1,000. It also carries bounds, so that you know how to convert it to a -1 to 1, or if you want to.
So you preserve the accuracy as long as you can.
Yes. You only can normalize and denormalize. So that was an overview of C-filter template. Now I'm going to go through the actual implementation of the sine oscillator inside Eigen-D.
So this is real agent.
This is a real agent inside Eigen-D. Got to sit down for this. Sorry?
Just take a deep breath.
Preparing myself.
So I've got several files open here. Probably interesting for you to see is where they are located. So you can see the plug synth directory where you have the sine oscillator plug.py file. That is that Python wrapper that you saw in the C-filter template. And you can see a lot of things that are actually the same as what I explained and Jim explained before. So you get again this agent is being set up, and you have one audio output. You've got this native implementation that we will tie into, your cookies being passed around, the clock domain that's set up, the splitter, and then you've got these inputs that have the same data types. What a coincidence. And then you've got your volume, frequency, and detune that then will be used by the actual implementation of the sine oscillator. So what the sine oscillator does is that it actually uses a wavetable synth implementation with a sine table, a table of values for the sine wave that it will actually iterate through based on the offset.
Has everybody here ever done a wavetable synth? Does everybody know kind of how they work?
Don't be shy, because I didn't until...
You didn't know, so you basically have a table of values, say for a sine wave, and then you calculate the offset to the value according to where the previous value was and the time tick that's actually happened. So you can go tick, sort of tick, 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 and you just pick that value out and output that value. So it's a very efficient way of going from a wavetable, which is in memory, straight to an actual output value. There's no sort of computational stuff involved. It's just, well, apart from adding up.
Yeah, a bit of interpolation.
Yeah, exactly. And then you have to do a little interpolation depending upon the resolution of your wavetable values.
You're saving yourself most of the math then.
Sorry?
You're saving yourself most of the maths.
Oh, there's virtually no maths. It's basically it's one calculation, and you might be linearly interpolating or doing some interpolation between the two. If you've got a wavetable that's at a sufficient level of resolution, you don't need to do the interpolation. That's a trade-off between memory usage and signal processing.
So that's, and then we got from the Python wrapper, which is almost exactly the same, to the actual header file again here, which is again which is exactly the same as what you saw before, right? Which then has an implementation here at the bottom. So this implementation here, this part here, which you will recognize again because it provides an input mask of signals, an output mask of signals that's being set up here at the top, right? Which correspond to the signals that have been set up in the Python wrapper. And so the only thing where it actually starts to become different from C-filter template is where it starts getting interesting, is when the C-filter controller creates the actual functor when the wiring is being done, right? So for each polyphony channel, it will set up a wavetable synth, right? So it instantiates this here, and it passes in the actual wavetable values. For those that have never seen that, you know, this thing that goes on, and the size of it is being passed into that implementation. And then it starts using that wavetable class. So then we get into the implementation of the actual wavetable, which just sets up a bunch of default values so that it can work without anything being connected. And then it's the same methods that you saw in the C-filter template. So start from start, which is this part here. So what it does is basically it starts with the default values, the default values for the different parameters of volume, frequency, and dTune.
So this is called on the beginning of the event?
This is called on the beginning of each event. And so you get the event ID being passed in, which is a regular data type, Eigen data type, which always has its timestamp of instantiation, which you can use to know when the event was actually started, which is being used here. So you can when you extract the timestamp, you can use that to get the latest value for the frequency that might already be in the event, in the buffer that's being sent along.
With a normal merge,
That sounded like a realization.
with a normal merge input, those initial setups shouldn't really be necessary because there's always going to be a value that the merge input has sent. It's just that if you should use this component with something that didn't implement the input at all, and didn't feed anything, then you might want to do something. But those internal defaults will often be never used.
And so you get the two different versions of basically starting up, which is getting the latest value. So start with a frequency and a detune value, and then reset so that your actual envelope for the volume can start from a clean slate, and it will start processing without having previous data in the buffer. So that is called at event start. Then each time the clock ticks, we'll call this method, right?
Even if no data is available?
Well, there is always data in the event.
Well, if it's started, hence the guard statement, if not on, return false.
If we're running an isochronous, you've got to be generating output even if there's no input. Even if your input signals aren't changing, you've still got to be pushing
if nothing changes, I just have two identical values with different timestamps.
But what you have to realize is this is basically initially being called by the clocking of your audio interface that needs samples to play, right? So this will always be called when an event is started, so that you get the opportunity to send out audio. If you don't want to send out anything and there is no data in the buffer, then well, you don't use the data that's in the buffer.
You can write an agent that doesn't send any output, so your input might not have any data.
It's actually, because C-filter's quite nice to use, and it's actually quite common to use it as a pure input with no outputs, because you just don't connect up its output to anything and don't make any events. But it's quite convenient as an event receiver.
Because it does the correlation for you,
or just because it does the event management.
So, and then we get the same thing that we saw before. You create, memory block of memory of floats where you will store the samples in. And this is actually the only real part that does the wavetable.
That's the whole synthesis, isn't it? Right.
That's the synthesis. So what it does, it takes the size of the table, and since that's one cycle, divides that up by the sample rate, and then multiplies it by the frequency you want to play it on, and then you can detune it. And that's where it actually knows what the increase is when it has to step through this table of values in the wavetable. So this increment changes based on the frequency of the note that you're playing and the sample rates.
You're allocating and deallocating that make norm stuff every time you come in through it.
This one?
Yeah.
This comes from fast memory, which is pre-allocated. So
I know it's a pre-allocated block, but it's still. Could you not just keep hold of a block?
Yeah, this is something that we talk about all the time. The thing is that buffer is going to be fed into a queue and might well end up in many different places, into recorders and stuff. And it seems better to allocate like that and then pass pointers to it around than use just an ordinary buffer. If our signals only ever dealt with audio buffers, then a more common technique in these things is to do this buffer switch thing, right, where each link is a pair of buffers and you do it and then switch the buffers over. But because our signals can carry all sorts of weird stuff, like dictionaries and variable length, they have odd stuff in, and often bits of them will get copied, stored, and it's easier to do it this way.
It was just it
is the case though with the isochronous data, we might be better off using static buffers, but that's actually a very tiny amount of our data flows.
And there's nothing weird in the code that would limit that. So if it did it wouldn't die. You just have to be careful with the normal stuff of making sure.
Well, these things might get copied and stuff. So it is an immutable reference counted structure, reference counted thing. That data.
It is reference counted.
Yes, it's just that the data NBs are not thread safe reference counted. So you need to be in the fast thread to deal with it.
So ref counting is not atomic.
So can it happen to me that while I am in my process method, the uplink agent still feeds in data to the buffer, so in one moment next signal returns false and in the next moment it's true?
No, the buffer will not be modified once you...
In that context, you get to crunch your buffer, I think.
Yes.
Currently there's only one fast thread, so the fast thread is single threaded.
So one tick, the buffer's always the same.
If we multi-thread the fast thread, so it can take advantage of multiple calls, that's going to be a problem that has to be dealt with.
So this is the basic synthesis thing. And then basically what it does, it kind of goes over the signals that have been fed in. It gets the next signal from the audio input, stores that as a current volume, which it would then use afterwards during the processing. And then it iterates again over the frequency and the detune inputs, where it actually recalculates that increment with the same formula. The increment that steps through the wavetable. And I don't remember what that there is.
An example of a log message there that's been commented out to Ultras.
Yes.
Jim, could you just tell us about logging? It's about the only debugging someone's got.
Yes. Well, yeah, you'll find a debugger isn't actually that much use in this stuff, especially in the fast thread, because what will usually happen is you'll hit a breakpoint, then your USB will fold up because you're not servicing the ISO buffers anymore. So usually we debug by logging. Log message has reasonably minimal impact because the messages are actually tossed over to another thread for output, so it doesn't cause the fast thread to hang up. So within reason, you can sprinkle log messages in the fast thread.
Don't leave them in there though.
Anyway, you like.
Production code, whatever you do.
They can slow the thing down though.
So what's this again? This is part of C-filter, isn't it?
That gives you the offset of this sample into the buffer.
Yes, so that you can use it afterwards to continue processing through the wavetable, right?
Confusingly, you know, the message called process.
And this is called several times because you can still have so data that is since you have to fill up the entire audio buffer during that clock tick. There might be no events, no signals anymore here. You might want to continue processing until you reached the timestamp of the to timestamp of that particular C filter process method. That's basically why this process method has been factored out. Then what this does, when it steps through the wavetable, it gets the value out of the wavetable through the interpolate method here. And the only reason there's the interpolation here is that because the inputs are floats and not integers, so you could have difference between the different indices in the wavetable array. And it calculates the linear interpolation.
When you get the process call, the to and the from will be the start and the end time of the ticks.
Yes.
But the data won't necessarily, you won't necessarily have data for all of that.
No.
So you might have to fill in, you basically have to fill in that.
The buffer, you have to make sure that if you wouldn't,
values in all those books.
right, if you wouldn't do that, you wouldn't,
Yeah.
But this is not, this is basically just the data that's available in the queue that you get passed in, right? There might only be one value on that, but you have to generate, in this case, the buffer, the buffer size.
Milliseconds, you're only going to get 5 or 10 of them. Yeah.
Okay. The buffer size has to be filled in, which is independent, really.
Yeah.
Right. But in this case, probably, the volume is being only processed here. So the volume is actually, in this case, the volume is only being handled at each clock tick, right?
Yeah. Mm-hmm. You're not doing the volume.
No, volume is not being done.
That's because
it creates
the volume is an ISO signal, so it's actually getting a whole buffer.
Right. So what it does for the volume is it gets an array of the volume signals, and then it will use those. So it passes this into the process method to actually multiply each sample with the actual generated sample. So you get the value of the sine wave out of the wavetable, which will have a certain value, which will then correspond to a particular sample of the volume at that point in time.
You don't do that if you use a single volume value for your whole buffer. Then at the clock tick rate, that frequency will appear in your output stream.
So that's basically it. If there's this volume array being passed in, it will match up the samples based on the volume value that it's got. And otherwise it uses the static volume that has been passed in. So that's why there's this if statement here.
So is that the case where you haven't got an envelope generator or something,
right.
You've just got a number that's been stuck on as default?
Which if you think about it, is if you're using it as an LFO, that's exactly as your amount. That's your volume of your output, that's what you're going to have. So.
And so then it generates into the output buffer here, which is being passed in to the process method here. Then we set up the scalar, as we saw, the scalar value, as we saw in the slides, which is this value here. So then we get to the final step of this presentation, that is, once you've written this agent, how do you distribute it? And that's the fun part, because it's really not difficult at all. Only thing you do is type make with mpackage as an argument. Inside your directory of your agent. And it will create a single installer file that you can take and give to anyone. People double click it, it installs it inside the specific contrib directory in the Eigen-D installation, and Eigen-D will detect it and use it, and it appears. So this is the installation file on Mac, for instance. It appears on the temp package directory. And just take that file, and you can hand it off or sell it.